Okay, so we went over solubility, we went over the polar nature of water. Okay, make sure that for your unit exam, you are able to explain to me what it means to be a polar molecule, okay, how that works, what happens with the electrons, the behaviors that might make a polar molecule exhibit, and at least one example, okay, like the trees being able to move the water up the trunk would be a good one, okay? So make sure you go over that stuff. That's kind of what's important about the polar molecule stuff. Okay, and obviously be able to use your solubility chart to determine whether a compound is soluble in water or not. That will be important for the next lab that we do as well. Speaking of the next lab we're going to do, the next lab we're going to do is going to be on chemical reactions. That's a good segue, right? So we need to go over the different types of reactions. And that's what we're going to do today, is introduce probably just a few of them. I don't know that we'll get through them all. Okay, we're going to look at how we write, represent, balance, etc., chemical reactions. Okay, this is probably the most intense or most important part of this unit. Okay, reactions kind of governs everything else. Remember that in order to be able to write reactions properly, okay, you've got to be able to write chemical formulas properly. So if that is something you're still struggling with, please make sure you come in and see me about that. All right. Chemical change. If there's a chemical change, how is that different from a physical change? If I boil water into steam, is that a physical change or a chemical change? Okay, why? I can't? Could I condense the steam back to water? You're right, a chemical change I can't undo. Boiling water into steam is only a physical change though, because it's still water. Okay? Whether it's in one phase it's a liquid, in one phase it's a gas, it's still chemically the same stuff. Physically it's different, it goes from a liquid to a gas. Okay? But chemically, I still have the same material I started with. In a chemical change, I have new materials. Not new elements, but new materials. Okay? Because remember, Dalton said that in a chemical reaction, atoms can be separated, they can be joined, or they can be rearranged. Okay? That's basically the definition of a chemical change. If one of those things happens, then a chemical change has occurred. Okay? If I change the state of something, or if I crumple up a piece of paper, that's just a physical change. It's still paper. Okay? I can get it back, right? But if I have a campfire, or I throw the crumpled piece of paper in the fire, that's a chemical change. Okay? I change the cellulose and whatever else is in the paper into carbon dioxide and water vapor. Okay? I'm not getting the paper back after that. Okay? So everyone kind of follow the difference. Okay. What are some of the signs, then, of a chemical change? If something changes chemically, what might I see? It could change color. Think about the campfire example. Temperature change, that was actually why I said think of the campfire. You wouldn't light a campfire unless you wanted to warm up. Okay? So there'd be a temperature change or energy change. Okay? Yesterday we watched this happen in a chemical reaction in the video with the weird Italian music. What formed? Precipitate could be formed, okay? Because I'm making a new substance that may not be soluble in water, even if the two things I started with were, okay? So these are things I want to look for, okay, when a chemical reaction occurs. Also, if I start out with two substances, I mix them together, and all of a sudden something smells, I made something different. The starting materials didn't smell, now there's a smell, okay? All of these things are indications that a chemical change or new materials have been made, okay? So, in a chemical reaction, this is what we're looking at. Okay, so let's say I have this. Okay, that would be an example of a chemical reaction. Now, right now it's not balanced, now it is, okay? Here's how a reaction works, and you might want to write this one down, just so you can kind of identify the parts here. So in a chemical reaction, the stuff we start with are called the reactants. Okay? Because they're the things that are going to react. Whatever comes of the reaction, or is produced, are our products. They're separated by an arrow. Okay? So a reaction is always written, here's what I start with, then there's an arrow to what I finish with. Okay, in that reaction, did I kind of obey all the rules that Dalton said I should? What elements do I start with? Or what elements are in my reactants? Right, sodium, chlorine, iron, and oxygen. Those are the 4 elements that I'm starting with. Do I end with those same elements? I do. Okay, so I obeyed what Dalton said. I didn't make any new elements. I made new materials, okay, because I rearranged, in this case, the elements that I had, okay, which is one of the things he says in his atomic theory can happen in a chemical change. Okay? These products will have very different physical properties than the stuff I started with. Okay, agreed? Okay, and that's why we see the signs of a chemical change, like a color change, an energy change, a precipitate being formed, an odor, okay, being produced, any number of things. Okay, they're all indicators that something has changed and it has new properties. Okay, that's what happens in a chemical change. All right, so in a chemical change, the final products are chemically different than the starting reactants, and the evidence we have could be an odor change, a state change, an energy change, or a color change. Okay, those would be important for you to know. Okay, if we go back to this reaction I wrote, okay, right when I first wrote it, I said it's not balanced, and then I put a 2 right here. What did I mean by that?
In the product, you add a 2 and Cl2,
Okay, in my products, there were 2 sodium atoms and 2 chlorine atoms. But before I wrote this 2 here, that wasn't the case, which means if I don't put a 2 here, I created matter. Can I do that? Okay, the law of conservation of mass, or the law of conservation of matter, whichever way you've been taught, it's the same thing. Okay, says directly, you cannot create matter and you cannot destroy matter. So I have to make sure when I write a reaction that I haven't done that. Okay, by ensuring I have the same number of each type of atom on both sides, the products and the reactants. Okay, otherwise, I've broken the cardinal rule of all chemistry. Okay. All right. So, there are 5 reaction types that we're going to go over. There's more than that, but we can kind of start out with these first 5. That's the only 5 we'll worry about in Science 10. Okay? So Dalton says atoms can be separated, they can be joined, or they can be rearranged. 3 of the reaction types we're going to go over involve rearranging. Okay? But the first 2 involve joining and separating. Okay? So the first reaction type we're going to go over is a synthesis reaction. Okay? And in a synthesis reaction, I join 2 elements together to form a compound. Okay? That compound could be ionic, it could be molecular, it depends what's reacting. All right, so our first example here, I start out with 2 magnesium atoms, and we don't worry about the states of matter in Science 10, but this little S means solid, so this would be like metal, magnesium metal, okay, plus 1 molecule of oxygen, okay, that contains 2 oxygen atoms, and that's a gas, and that's going to create or form magnesium oxide, which is a black kind of, it's almost like tarnish. Okay, if you've ever seen what a silver tarnish looks like, it kind of looks like that. Okay, and it's magnesium oxide, and it's a solid. Okay, now if I look at my reaction here, on my product side, how many magnesium atoms do I have? 2. Okay, this 2 here means there's 2 molecules of magnesium oxide. If there's 2 molecules of magnesium oxide, there's 2 magnesium atoms and 2 oxygen atoms. And over here, there's 2 oxygen atoms and 2 magnesium atoms. Okay, so I haven't created any matter, I haven't destroyed any matter, it's all balanced. Okay, similar thing with this reaction down here. Okay, I start out with 2 potassium atoms. They react with a single molecule of bromine, and they form 2 molecules of potassium bromide. Okay, all the things we start with are accounted for. Okay, we've just had 2 reactions where we have elements that come in the form of a molecule. Okay, there are a number of elements on your periodic table that do that. We call them the molecular elements. Okay, and they are everything in group 17, phosphorus and sulfur and hydrogen. Okay, so that's something you'll have to remember. You may want to write it down. Okay, all the stuff, all the non-metals in group 17 come as pairs. Okay, so that's O2, okay, and F2, Cl2, bromine, okay, iodine, they all come as 2s. Okay? Nitrogen and oxygen also come as 2s. Okay, so you kind of make a big 7 here. Okay? And oddly enough, there are 7 of them in it. Okay? The big 7. Okay, so nitrogen, oxygen, chlorine, bromine, iodine, and astatine all come as 2s when they're by themselves. Phosphorus comes as a 4 when it's by itself. And sulfur comes as an 8 when it's by itself. Okay, hydrogen also comes as a 2. Right, so looks kind of like this. Like we got, if someone says phosphorus reacts with something, it means that reacts with something. If it says something reacts with sulfur, that's sulfur. Okay, if it reacts with oxygen, nitrogen, chlorine, bromine, okay, they all come as 2s. Hydrogen, when it's by itself, comes as a 2. Okay, they're just things that we have to remember. They are the molecular elements. Okay, if you didn't write those down, you really, really should. Okay, need to know which elements come as pairs. Okay, so you got the big 7, phosphorus, sulfur, and hydrogen. Okay, so there's 10 to know. So atoms can be joined or they can be separated. Okay, so the reaction that separates things we call a simple decomposition reaction, because decomposition means to break down into simpler parts. Okay, so in a decomposition reaction, a molecule or a compound breaks down into smaller parts, usually into its constituent elements. Okay, so we're looking at, in this case, water being broken down into hydrogen gas and oxygen gas. Okay, or in this second example here, I've got 2 molecules of nitrogen triiodide. Okay, it would look like that. And it's going to break down into nitrogen, which when it's by itself comes as a 2, and iodine, which when it's by itself comes as a 2. Okay, so it would look like this when it's broken down. Okay, that's why it's important for you to know which things come as a 2 and which don't, so that when you're writing reactions, you know whether to put a 2 beside them or not. Okay, questions on the decomposition reactions? Okay, so what's going to be required of you going forward is if I show you a reaction, you're going to be able to tell me what type it is. Eventually, it's going to come to, I only show you this part, just the reactants, and you're able to tell me what type of reaction it is. You will be able to do that because they all start different. Right, for example, synthesis reactions always start with 2 elements, okay? So it's easy to tell, okay? Decomposition reactions always start with 1 compound, okay? So they're easy to identify. Okay, so on your periodic table, remember we identified, okay, these ones here, okay, and so we need to remember those, okay, as well as phosphorus and sulfur and hydrogen over here. Chris, you can. Okay, I'm going to give you a 3-minute break before I go into combustion reactions, because combustion reactions are probably the trickiest of all of them. We got to talk about how we write them, how we balance them, and all of that. So I'm going to give you a 3-minute brain break, and then we're going to go into that. Okay? So for combustion reactions are kind of the one reaction that's really different than all the others. Okay? They have their own rules for how they work and how we balance them, how we make sure there's the same number of each element on both sides. Works differently for these reactions than all the other types. Okay? So, first off, in a combustion reaction, something, usually a hydrocarbon, is burned completely in the presence of oxygen. All right? That's what you're seeing in this reaction right here. Okay? C3H8 is a hydrocarbon because it contains carbon and hydrogen. Okay? That particular hydrocarbon is propane. Right? So this is the reaction that would go on in a barbecue. Okay? In a propane barbecue. So the propane burns in the presence of oxygen. The products of all combustion reactions, regardless of what hydrocarbon is burning, are always the same. All that changes is how much of them I get. And those products are always carbon dioxide and water. Okay, now, this is a bit of a simplified example, and that's all we're going to deal with for hydrocarbon combustion, because it is complete. Most of the time when we burn stuff, it's not complete, and we get byproducts like carbon monoxide, which is deadly, okay, and other types of things. But we're going to simplify and just say this worked perfectly, and it made only carbon dioxide and water. Okay? So those are always the products of any hydrocarbon combustion reaction. Okay? This is why on a really cold day, if you're behind another vehicle at a stoplight, sometimes you can see water dripping out the tailpipe. Okay? It's because water is one of the byproducts of hydrocarbon combustion. Okay? The smoke you see usually contains this, okay? Carbon dioxide, as well as water vapor. Does everyone follow me there? Okay. So in this reaction here, I need to check and see that everything is balanced. All right? How many carbon atoms are there right here? 3. Okay, the little 3 says there's 3 carbon atoms. How many carbon atoms are there over here? Still 3, right? I've got a big 3 in front of carbon dioxide. That means there's 3 carbon dioxide molecules. That means there's 3 carbon atoms. All right, how many hydrogen atoms are there? 8, okay? Over here, how many hydrogen atoms are there? 8, 4 times 2 is 8. All right, now here comes the tricky part. How many oxygen atoms are there right here? 4. How many here? 6. What's 4 plus 6? 10. How many do I have over here? 10. Okay, so these big numbers that we write in, they're called coefficients. They mean multiply everything in the compound behind me by this number. Okay, so we can figure out how many atoms there are. So in a combustion reaction, okay, so let's do one that looks like this. So write this one down, we'll use it as our first example. So in this reaction, I have pentane, okay, C5H12, reacting with oxygen, and that's going to produce carbon dioxide and water. When I balance, in the process that I go through, a combustion reaction, I balance it in alphabetical order. So that means I start with carbon. How many carbon atoms are there here? 5. Okay. How many are there on that side? Just 1. Is that a problem? Okay. How do I fix that problem? Yeah, put a 5 in front of it. This I can do, okay? I sometimes have people do this. Can I do that? Is that carbon dioxide anymore? No. Okay, I can't change the compound itself. I can change how much of it there is, but I can't change the compound itself. So once the reaction is written, all I can do is put the big numbers in, okay? Because that changes amounts. It doesn't change the actual materials. All right, so by doing that, I've now balanced my carbon atoms. Okay? What comes next in alphabetical order? H or O? H. Okay, so I got to do H next. How many H's are there here? 12. Okay. How many here? What needs to go here? Okay, now my hydrogens are balanced. Now I need to balance my oxygens. Okay? How many oxygens are there on this side? 16, okay? You got to treat a reaction like it's math, okay? 5 times 2 is 10, plus 6 more is 16. Okay, so I've got 16 oxygen atoms on the product side. I only have 2 on the reactant side, so what needs to go here? 8, yeah, 8 times 2 is 16. Now it's balanced. Okay, got the same number of everything on both sides. Okay, do you have to do a little bit of math? Yes, but it's like grade 4 times table math. Okay, it's not hard. Okay, but we do have to do a little bit of multiplication to make it work. All right, so the first rule of balancing a combustion reaction is. So, okay, so the first rule is balance in alphabetical order. The second rule, we sometimes call the rule of two. If you're a Star Wars fan, that's what we're referring to. Okay? Rule of two. Okay? If there's an even number of carbons, we start the reaction with a 2. Okay? So. So we're going to do an example that requires us to use both rules. Okay, so that'll be this. Okay, so if I start this just alphabetically, I'm going to run into a problem. But we'll walk through it to see what that problem is. Okay, how many carbon atoms are there here? 4. 4, okay. So if I just start doing this like I did the last one, I'm going to put a 4 there. Okay, how many hydrogen atoms are there? 10, okay. What do I need to put here? 5, yeah. Here's where I run into my problem. 8 times 2, or sorry, 4 times 2 is 8, plus 5 more is 13, yes? What times 2 is 13? Well, 6 and a half. Yeah, but no whole number. Okay, can I have 6 and a half oxygen molecules? There's the problem. Okay, that is why we have the rule of 2. Okay, so this is not going to work. Okay, I have to change this, and I have to start with an even number. Okay, so as soon as I see this even number, okay, I know I have to start with the rule of 2, and that is I start with a 2. Okay, everybody with me here? Okay, so you hear Yoda's voice in your head. Okay, an even number of carbons you have. Start with a 2, you must. Okay, so we go here. 2 times 4, so you're never going to forget it now. Okay, like I'm totally willing to embarrass myself to make sure you don't forget it. Okay, all right. 2 times 4 is 8. All right. So now I go here. Whoops, that's supposed to be an arrow. Okay, I put an 8 there. Now my carbons are balanced. Okay, 2 times 10 is 20. All right. What do I need to put here? 10. All right, now if I look at my oxygens, 8 times 2 is 16. 10 times 1 is 10, so 16 plus 10 is 26. What times 2 is 26? Now it works. Now I have all whole numbers. Don't have any decimals. Those are the special balancing rules for combustion reactions. Okay? All our other reactions balance way easier than that. Okay? For every other type of reaction, all we have to do is go start with the biggest number and balance from there. Okay? It's really straightforward. But combustion reactions, they have this problem that we always run into, so we balance them off of that. Okay. Questions on that? All right, the last two reaction types are very similar to each other. They're replacement reactions, so they're another example of rearranging. Okay, the whole separating, joining, rearranging. So in a single replacement reaction, okay, what we have is we have an element, either a metal or a non-metal, reacting with an ionic compound. Okay, so replacement reactions always involve ionic compounds. There will never be molecular compounds in a replacement reaction. Okay, so I have, in this case, a metal, copper, reacting with this ionic compound, silver nitrate, okay, and that's going to form silver and copper nitrate. So, did something get replaced? I started out, copper was by itself, silver and nitrate were together. When it's done, silver's by itself, copper and nitrate are together. Okay, so something got replaced. What happens in a single replacement reaction is that element that's by itself replaces the part of the ionic compound that it's similar to. So since this was a metal, it's going to replace the metal. If this was a non-metal, it would replace the non-metal. Okay, so all that happens is copper and silver switch places. Okay, when you can actually do this reaction yourself, okay, I think they might even do it in Chem 30, okay, where you take, like, we used to take pennies, okay, back when pennies were in circulation, okay, now we just take chunks of like copper wire, and you stick it in a solution of silver nitrate. And if you leave it over a day or two, when you come back, the penny would be plated with silver, okay, with pure silver. Right? And that's because the copper would knock the silver out, okay? And the silver would plate out, and the solution would start to turn what color? Blue. Yeah, right? All copper-containing compounds are blue. So you'd start out with a penny in a clear solution, and after a few days, you'd have this penny, but it would be covered in silver in a blue solution, okay, as the reaction would go on. Okay, now you're probably all thinking, okay, so that's a way to take copper, which is cheap, and make silver, which is pricey. That's like alchemy, and we're gonna get silver nitrate. Okay, well, the thing is, silver nitrate is expensive because it has silver in it. Okay, and obviously this reaction could produce silver, so yeah, we don't have a lot of that on hand because it's expensive. Okay. All right, does that idea make sense? Okay, so in any single replacement reaction, one thing gets replaced. Okay? It replaces the part of the ionic compound that it's like. So it could be like this with the metal replacing the metal, okay? Or it could be like this. I might have okay, if I had these two things reacting, that's still a single replacement reaction. I've got an element reacting with an ionic compound. Nitrogen is a non-metal, so what part of this compound is it going to switch places with? The oxygen, because the oxygen is the non-metal. Okay, so what's going to happen is I'm going to get oxygen by itself, and I'm going to get magnesium nitride. Okay? Single replacement reaction. Replace the thing that we're like. Okay. Is this reaction balanced? It is not. So, I don't follow the same rules as I would in a in a combustion reaction, okay, I go with the biggest number. What's the biggest number in here? Okay, what's the biggest number? Yeah, like 3. 3 is the biggest number. Okay, and it's on magnesium. So on this side, there are 3 magnesiums. How many over here? Just 1. So what needs to go here? Okay, if I put a 3 here, is that going to make it really hard to balance my oxygens? Okay, so is there a low, like, common multiple between 3 and 2? 6. Okay, so got to do a little bit of math here. I'm going to put a 6 here. Okay, what do I need to put here then? 2. Okay, so now I've got 6 magnesiums. 6 magnesiums. How many nitrogen do I have? 4. So what needs to go here? Right, and what's still left to balance? I got how many oxygens here? 6. How many here? Done. It's balanced. Okay. Start with the biggest number, go from there. Okay. Sometimes you have to erase and pick a different number, but it becomes pretty apparent what number that needs to be as you go along. Okay. So that's what we're going to be working on next week. Okay. Lots of reactions, working on writing, balancing, identifying the types, and then we'll even move into predicting reactions. Right? But we'll leave it there for today, because what do we got here? Oh no, we still got time. I was thinking it ended at 9:25. Okay, we still got time. All right, let's look at the last one. We'll get all 5 covered. Okay, last one is double replacement. And even though that would imply that it's more complex, they're actually easier. Okay, in a double replacement reaction, you have 2 ionic compounds reacting with each other. And all that happens is the metals switch places. Okay, so in a double replacement reaction, you get 2 new things, okay, but they only come from the metals switching partners. Okay, so on this side, I start out with calcium chloride and sodium carbonate, and on this side I have calcium carbonate and sodium chloride. All that's happened is the metals have switched partners. That's all that happens in a double replacement reaction. Okay? Oftentimes, in a reaction like this, you will get a precipitate forming, because you're going to get 2 new ionic compounds, one of which may not be soluble in water. Okay? 2 of the reactions we do in our reactions lab are going to produce precipitates. Okay? There'll be double replacement reaction and a precipitate will form in them. Okay, let's try one here. Let's go with that's a double replacement reaction. Lead 2 nitrate reacts with potassium iodide to produce lead 2 iodide and potassium nitrate. It's not balanced. What should I balance first? How many leads are there here? 1. How many nitrates are there? 2. 1 potassium, 1 iodine, 1 lead, 2 iodines, 1 potassium, 1 nitrate. So the biggest number is 2, and it's on 2 of my items. There's 2 iodines, there's 2 nitrates. Does it matter which one I choose to balance first? Makes no difference. I'm supposed to start with the biggest number, and there's a tie. Flip a coin. Okay, makes no difference. I'm going to start with nitrate just because it starts first. Okay, so on this side there are 2 nitrates, and over here there are only, or is only, 1. So what needs to go here? 2. When I put this 2 here, does it apply to the potassium? How many potassiums are here? Just 1. What needs to go here? Okay, when I put that 2 there, it balances my iodines as well. Okay, so my nitrates are balanced, 2 and 2. My iodines are balanced, 2 and 2. My potassiums are balanced, 2 and 2. And my leads, 1, 1. Got it. Okay, start with the biggest number and just go back and forth until everything is balanced. Okay? All right. I want you guys to try, because we just went over that. Okay. I want you guys right now to not pack up, and I want you to tell me what kind of reaction each of these are. Okay, so tell me, is it single replacement, double replacement, combustion? Okay, tell me what it is, and see if you can balance. Okay, what kind of reaction is the first one? Somebody be brave. Synthesis, yeah. 2 elements are combining to form a compound. So that's a synthesis reaction. All right, if I want to balance it, I start with the biggest number, which is hydrogen, a 3. There's 3 hydrogens on this side, and there's 2 over here. What's the lowest common multiple that I can use to balance? 6. Okay, so what needs to go in front of this hydrogen? A 3. What needs to go in front of that hydrogen? Okay, when I do that, does that make my nitrogens work out? Always a good sign. Okay, if you balance one thing and it puts something else into balance, you're doing something right. Okay, all right. What about this second one? What kind of reaction are we looking at there?
Single replacement.
Single replacement. We got an element reacting with an ionic compound. Okay, what should I balance first? Reed, what should I balance first? What's the biggest number? The 3. Okay, so I'm going to balance my calcium first. There's 3 on this side. Now there's 3 over here. Okay, how many chlorine does that give me? 6. What needs to go over here? Is it balanced now? It is. Have a good weekend, but not too good. We'll see you on Monday.